Okay, I think now it's time. Now it's time to say good noon. It's not afternoon. It's not morning. So it's noon. Yeah, my name is Xiaodong Duan. I'm a researcher from Aarhus University, and today I'm going to present some work of utilizing the data we collected in BeeGood project to predict the colony health status using machine learning methods. So I hope it's not so boring, but if it's boring, then Martin maybe can help me too. Yeah. So I think at least for myself, if I decided to do something, before that, I need the motivation. I need to know why I want to do this. Otherwise, why bother? So you saw this picture from Dick's presentation in the morning. The honeybee colony declines and losses are a serious problem, not only in Europe, but also in globally. So what we want to do here, we want to help with this problem. And we can think like in this way, I mean, as we as human, when we get sick or we feel uncomfortable, we will go to the doctor to get help. Then the doctor can help us to have some further diagnosis or to give us some treatment to help us to recover from our current situation or to improve our health status. But unfortunately, bees, they can't communicate themselves to us directly. They can't just tell us something wrong is with me, with the colony, please help. They can't. So that's why we want to develop a tool that can speak for them. That this tool should be able to monitor the colony development and give us warnings as soon as possible, because we need early warning. If it's too late, then even with the help from us, the colony can't recover. So time is everything, and timing is very important here. So if it's late treatment, I'm thinking no help at all. So that's the motivation. Now let's do it. So the digital tool essentially is a monitoring system. So the first step, of course, we need a colony. And then we install a bee base beneath the hive to monitor the hive development. And from this bee base, we can gather different types of data, like the hive weight and the inner temperature and the out temperature, and etc. So after we have this data, we can train a machine learning model. So here is an example. It's a neural network. I will show you some more information later. So after we train this model, we can deploy this model into the Beep app. Then for the new colonies with this Beep base, we can continually monitor the system, monitor the colony development, and give us warnings about the survival rate of the colony. So if it's a good status, then nothing needs to be done. But if the survival rate is predicted very low, then we need to do some further inspection about the colony to see where the problem is and how could we help with the colony development. So as you can see from this figure, the key components of our method is first the data collected from the BeeGood project and also the machine learning model. So now you might wondering what they are. What are data-driven method? What are machine learning method? So for data-driven method, they involve harnessing the power of data to inform predictions and also actions, etc. And machine learning method is a key tool in the realm of data-driven method. And for machine learning method, is a subset, is a special subset of artificial intelligence method, which use data to build model, to train model, to help us to understand better about the data we have, and then to make predictions or decisions without being explicit programmed. So it's not a rule-based programming. It's not like if this happens, do this. If this happens, do this. It's purely learned from the data. Now, so this is machine learning. So I think why we choose this, you might ask. Why we opt this machine learning method, not some other methods? So the first reason is because we don't have comprehensive knowledge about this problem, like the bee colony health status. You heard from Dick. We know many stressors can cause the colony, can cause trouble to the colony development, but we don't know exactly how they connected and which play a more weight and at some specific time. So it's if we know this very well, then we can have a very straightforward method to do this. We don't need to learn from the data. We can already make the predictions based on our knowledge, but unfortunately, no. And also, machine learning method has been proved a powerful tool in many applications. Like you might use them a lot in these days, like the face recognition, speech recognition. If you can talk to your phone, and also the phone can recognize you by your face image. And also, you might know the ChatGPT, which is an excellent example of how machine learning revolutionized the natural language understanding and generation. So it's a powerful tool, and we want to apply this tool to our problem. And the third reason is we can do continuous improvement. If we have new data, we can always retrain the model on the new data. Then the performance of this model can be improved. So this is the reasons why we want to try machine learning method on the bee colony health status prediction. Now, how could we do it? So how to use machine learning method? This is the procedures I usually follow to a new application for machine learning method. So first, first step is to define the question. So what we want to answer from the data. For example, for the face recognition is you give a facial image from one person. You want me to tell you his name, recognize him or her. And then the next step also I think is the most important step is the data. For this data-driven method, the performance really depends on the amount of data and also the quality of data that we have. And fortunately, we have the data from BeGood. We have collected a large amount of data, not only the automatic data, but also inspection data. So we need to prepare this data because this is the input to the model. Based on this input, the model will give the predictions. And the next step is to select the model. We have many different machine learning models available now. And we need to find the right models for our problem. Here, later, I will show you 3 different models I have tried for the machine for the data we collected in BeGood. Then now we have the model and also have the data prepared for our problem. The third step is we need to train the model. You can so the model has many parameters. We need to find the proper value of the model parameters, which works best on the training data. That's how we estimate the model parameters based on the data. So now the model is trained. The final step is to utilize the trained model. So here is we shift the model to Beep, and Beep can deploy this model to their Beep app. And then we can making predictions on new data. And also based on this feedback from the users, we can also improve the performance. As I said before, it's a continually improvement about the model. So let's follow this procedures to see what we did on the data collected in BigGood projects. So first, let's define the question we want to answer. We want to get the answer from the data. So the question is, can the colony survive after winter? Then we can turn this question into a classification question, classification problem. So after winter, the colony can be either dead or survived or being alive. So we want to predict this based on the data we collected from the previous year to predict the chance that the monitored colony can survive, can still be alive after winter in the next year. And we want to do this as early as possible, because I mean, we need to help the colony as early as possible. Otherwise, it could be too late. So this is the question we want to answer from the data, and also we have defined the problem as a classification model. So let's see the data. So this is the two types of data collected in BigGood. First is the automatic data from BigBase. So for this study, we mainly use three types of the automatic data. First is high weight, and then the inner hive temperature and out hive temperature. So these three types of automatic data we collected from BigBase. The second type is the inspection data. And in this study, we focus on these three types of inspection data. First is the varroa count, and then is the lip field method results, and also the disease data. So now we have the data. We need to prepare the data for our specific purpose. So we need to label this. First, we need to label this data as positive or negative for the classification model. So here is how we label the data. If a colony was dead after winter, the collected data from the previous year for this colony is labeled as negative. Otherwise, if it survived, then we have the positive data. So now we have labels for the data. What we need to do is we choose the model we want to test, and then train the model based on the data we collected and estimate the parameters for the model. So let's start with the varroa count data. So for the varroa count, it was done at least once per month from March to December. So at least then we have 10 numbers for a colony. And if we have multiple counting in one single month, we use the average number for that month to represent the varroa count number for that colony. Then we have for each colony, then we have a 10 elements vector. So we can use this 10 elements vector to do the prediction and the training. Here I have an example here. So that's 2 colonies. And these are the numbers for the varroa count at different months. So one colony, I can tell you one colony was dead after winter. One colony survived after winter. So based on this figure, can you tell me which one was survived? Just give me a guess. No, red. Yeah, so that's some kind of indication for the machine learning model results. So what I have tried here is I use a simple neural network. So this red nose is so each red circle is a number of the varroa count, like this one, and etc. for the rest. And then this green is a hidden layer. So that's the nodes to calculate the results based on the input. So this blue one is the output, the survival rate, or the label for dead or survival. So I use this to train use this 10 elements vector to train the model. And you can see, so we need to have 1 year data to do one time prediction. So this is the accuracy. The accuracy is calculated the total amount of data we have and the number of right prediction. So we only have 66.7% accuracy. So it doesn't look very good. And also from the figure, you can get the feeling, I mean, it's not very predictable. And the reason, I think, is because it's a cost data. The dynamic of the colony development is really complicated. But here, we only have 10 times check about the colony. So it's not enough. Sometimes we have a very high overall count, but it can recover if they don't have any stress from other resource. If they don't have a large amount of virus, they are not stressed by any other things, then they can recover from the overall count. So only use overall count is not enough, and also it's too coarse. And also we have some human introduced noise, because this count is done by us manually. So you can't be sure we have count. I mean, the counted number can represent the real overall number in the colony, even for the checking time. So that's why it doesn't work very well. So let's go to the next Liebfield method results. So for the Liebfield method results data, we have the estimation of number of adult bees, honey cells, pollen cells, capped brood cells, open brood cells, and drone brood cells. So in total, then for each inspection, we have 6 numbers. And this was done 3 times per year. So you can see, again, I give you some examples here. Spring, summer, fall. And I normalize them from 0 to 1. So 1, that means they have the very large number. And then if it's close to 0, that means the number is very low. So you can see here, so red is one colony, and the blue is another colony. So also, one is dead and one survived. Here again, the red one survived. But still, I can't tell you why. But that's how it looks like. We need to do more analysis about them, to real check for this colony what happened to it. But for me, it's what I can get from the data. I'm a data engineer, so if I need to know why. So maybe Nuno can help me with that. Yeah, so you can see I still use the same model, the neural network. The accuracy is really low. It's only 33% right. Again, because the Liebfield method is still coarse data. It's only 3 times per year. So it's not dense enough. It can't capture the whole dynamics of the colony development in a year. And also, it's for this type of method, I think compared to the overall count, we even introduce more human-introduced noise, because it really depends on the person who do these inspections and do the calculations. So it's not an accurate estimation for the numbers of we want. And also, it's an invasive activity to the colony. It could introduce new stress to the colony, but actually we didn't gain a lot from it. And I also believe if we can do this like every day, I think the results will be improved, but the colony might all die because of stress introduced from this leaf field method. Okay, so let's move to the next inspection data, the disease data. So again, this each colony was sampled 3 times per year, spring, summer, and fall. And for this study, I used the number of virus for this 6 type of virus. And they were classified into 4 categories: negative, low, medium, and high. And here one is X. That means we don't have data for this virus at this for this sample. And here I have 4 colonies: colonies 1, colony 2, and 3, and 4. And each row, the first row is the sample results for the spring, and then the next one is summer and fall. So then we repeat spring, summer, and fall. And also for this 4 examples, 2 colonies was dead after winter, and 2 colonies survived after winter. Again, red means survived. So I tell you the answer. But still, even you know this answer, based on this various data, can we tell that? Can we really, discriminate them to survived one and dead one? For the survived one, you can see they have some of them, they have very high infection of SBV, but still it recovered. So that's the results I tried for the neural network. So if I use the whole the data, all the data for the 3 times sampling, you can see the results is very low. But if I separate them, so I use the spring one to do a prediction independently, and then the summer one and the fall one. So the performance was improved a bit, but still it's not very good. I think this is same reason. This still some cost data, and only 3 times. It's only it's only indicates the status of the colony for the virus at the inspection time. So it can't represent for the whole year development. I didn't say, this data are not important. This data is quite important, but it's not enough to do the prediction for us. And also this will introduce some extra cost. Not every beekeepers wants to do this 3 times per year, unless maybe if we can predict the survival rate of the colony is very low, then they it's a good time to do this and to check which is the reason for the low survival rate. And also, I said, it's time dependency. It really depends when we did this test. So, okay, that's what we get from the inspection data. Let's move to the automatic data. Let's see how this automatic data works. And the data was recorded every 15 minutes. And also, thanks to beep, so we can change this interval for the data recording time. And for this study, all the data was averaged into hourly data. And if there is some missing data, I interpolate based on the history to get the full data for a colony. For the automatic data, first difference to the inspection data is a continuous data. So after we install the base, and then we can always get the data if the internet connection is good so it's a very dense data. And also it can encode enormous information about the colony development. So for example, the population size can change the weight, right? If we have a large population size, the weight is larger. If we don't have many bees in the colony, of course, the weight could be very small. And second, the foraging activities. If they bring a lot of resource back into the hive, of course, the hive weight will increase. So let's see if we can get good results from this. So first, this is an example from the weight data. This is raw data. I didn't do any pre-processing. So this is the weight and 2 colonies. Again, this time red colony survived. The blue one died. But you can see there's difference between. And this is the in-hive temperature. The red one survived. The blue one died. Again, but this can't tell much because it really depends on where we put the sensor, because we only have one single sensor and where the brood is. So it can differ. This is the out-hive temperature because these 2 colonies in the same place. So of course, they should have very similar out-hive temperature. So this one, so here I tried 2 models. So first, we still use the neural network and also try the support vector machine. So basically, you can treat this for this method. We want to find a line to separate the 2 classes. So I used each month I train a classifier for itself. So each month has its own classifier, and also we predict only once by the end of the month. So you can see here. For the in-hive temperature, it's okay. But the weight with the neural network in September, it achieved the best results. And we have also tested some combinations, but still it suggests that the weight is the most powerful data that we can use for the health status prediction. So can we do better? Because you can see here, in May, 27.8%. That's not good enough. In September, we have good results. Maybe it's too late. So that's the next method I have tried, because for the PRAISE model, they don't capture the time dependency for the sequential data we collected, because all the data, I mean, the weight, the in-hive temperature is sequential data. And here I try this model, which is able to capture this. So you can see this xt is an input to the model. So if we use the weight, then it's a weight at time t. And we have 2 hidden states. That's the driver within the colony. We can treat it like this. So what we want to do is we want to capture the dependency at time t to the previous time t -1. So hopefully we can get better results for the May, so we can have early warnings by then. And for this, we have the data from the past 9 days, and plus today's data is used as the input. So we only use 10 days data, and we do this prediction every day continually. So, and we also did this, I mean, to each month has its own classifier. So May has its own one, June has its own one, and the data is used is the data from the past 9 days plus the current day. So here's the results. As you can find, we have a huge improvement for the results in May. Before it was around 27%, but now it's about 70%. So it still is, I mean, it's not like a 90 or 100, but still I think it's a good enough to make the warnings. Then we can do more inspections, like to do the viral count or to get to have some sample from the colony and do the disease analysis. Then we can have a real picture, because this what I'm talked about. I can't tell you what's wrong with the colony. What's the reason for the colony that is not developing well. That relies on the inspection. So you need to do the inspection to find the real reason and then take the right action to help the colony to recover from the stress. So inspection data is very, very important, but we need to use it in the right way, because when the colony is developing very well, we do the inspection, it will not help. We can't find any problem. But if from the automatic data, there is a warning, something wrong is happening, please do the inspection. That will help a lot to the colony. And also for the in-hive temperature, if we use the in-hive temperature, we also get some improvement. But as again, it suggests the weight is the most powerful data for this prediction, only for the prediction, but not find the real reason. And then I try something else, because I want to see if we have one classifier for the whole year, so we don't have multiple classifiers for each month. How the results looks like, but as you can see here, it's getting worse. I think this is because in different months we have different stress source. So then they have different patterns. They can cause different patterns on the wave dynamics, on the high weight dynamics. That's why we need, if we want to have a better results, we need to have multiple classifiers to do this. I think it's okay. I mean, if we can have this around the 70 or 80% warning, let beekeepers to double check, it's good enough. So here's some conclusions. So for this specific application for the health status prediction, in general, automatic data achieved better results. The reason is because it's dense and continuous data. So it's always monitoring the hive development. And also it can capture the colony development dynamics. As I said before, almost all the things happening on the colony can change the hive weight. And the inspection is a measure of a single stress at a specific time. So we need to use this automatic data to guide us when we should do which type of inspection to test what happened to the colony, what's the reason for the colony dying. And also the second point is the automatic data have different prediction accuracy at different times. That's why we have different results in different months. So that suggests us to deploy multiple models. So for example, every month has its own model for the warnings. Then we can have better results. Again, I mean, hive weight is the most powerful measurement for this specific prediction problem. And here's the future work. So I talked to a team. I transfer the first model to BIP, and then they can deploy this to their app. Then we can test the results, and based on these results, we can always retrain the model. As I said before, we can always, one reason we choose to use machine learning method is because we can always improve the performance when we have new data. Thank you.